For today, we're going to be dealing with a particular special case of 2D kinematics I call zero launch angle. Now, we've already said when we're doing 2D kinematics, pretty much all our x equations reduce to this, or are 0 equals 0, so they aren't important. And these are the y equations that we tend to use. Zero launch angle means that our initial velocity is horizontal. Now this is simpler because that means we don't need to break down our initial velocity into x and y components, or rather, I guess we do, but it's much simpler. If our initial velocity is horizontal, that means that our initial velocity, the y component of our initial velocity, is 0. And the x component of our initial velocity is just the magnitude of that initial velocity. If you wanted to think about it in terms of angles, this would be our initial velocity at 0 degrees from the horizontal. So then our components would be initial velocity cosine 0, initial velocity sine 0. Cosine of 0 is 1, the sine of 0 is 0. So our initial velocity is just v naught, comma, 0. Now this makes a lot of our math much easier, because we have a v naught y here that becomes 0. We have a v naught y here that becomes 0. We have a v naught y hidden in this delta v that is also 0. Now on a test or quiz, these more general equations, actually I won't even, the more general equations that you saw all through last unit are the ones I'm going to be giving you. But you can recognize that if the y component of your velocity is 0, then that'll go away. So I'm going to write down equations for this case, but these aren't equations that I'll give you on a quiz or test. I'll give you the more general equations that you'll then have to break down. But with this simpler case, our x component is still the same. In the y direction, well, our acceleration in the y direction is g downward. I'm going to be using the convention that down is negative and up is positive. So that's a downward 9.8 meters per second squared. And delta v, that's a v final y minus the initial y, which is 0. So the acceleration equation reduces to this. Our time-independent equation is 2 times the negative g, so I'll put the negative out front, 2g delta y equals v final y squared minus 0. And maybe most importantly, the time-dependent equation becomes delta y equals minus 1/2 gt squared. Notice that this is exactly the same equation that we had used when we were just dropping an object in the lab where we dropped tennis balls. This is what we used to determine the acceleration due to gravity. And for an object thrown horizontally, the y component of the motion is the same as if we just dropped it. So let's do some example problems where we use these equations. Let's say, first let's do some ratios. Say I throw an object horizontally from height h with speed v naught. And it takes time t. How long would it take if I instead threw it from height 2h with the same initial velocity? Now, this is one of our ratio questions that everyone loves so dearly. Well, how much time? Well, how much time? That sounds like a question for the time-dependent equation. Our time-dependent equation is right here. So our delta y, we're thrown from height h, our delta y is going to be negative h. It's going downward, distance h. So that is the relevant equation. You can see the negative cancels out. So if we throw it from height 2h, then we have 2h is equal 1/2 g times some amount of time that is unknown squared. And we can, as always, divide these two equations to see what we get. H divided by 2h gets us 1/2. On the right side, 1/2 g and 1/2 g cancels out, leaving us with t squared over t2 squared. And we do a little bit of algebra and multiply this 2, cross multiply. We get t2 squared equals 2t squared square root, and that time is equal to root 2 times t. Right? I can keep asking you all sorts of questions like that. So keep in mind those ratio type questions are still available. Now let's say I throw a ball with horizontal velocity 5.7 meters per second from atop a building that is 7.5 meters tall. How far from the base of the building does the ball land? Okay, well, how far from the base of the building? As always, again, I recommend that you pause, see if you can figure this out for yourself. How far from the base of the building? Well, that's a horizontal distance, so we're trying to find delta x. We really only have one equation that we use to find delta x, so got delta x equals v naught x, which is just v naught, times t. Uh-oh, we don't know t. So how can we find delta x? Okay, this is something that happens often in 2D kinematics, is that we'll want to find something in the x direction, but in order to do that, we need to find time. In order to find time, we then go to the y direction to figure it out. We're looking for where it lands. That's when it hits the ground. So when it lands, we can apply this time-dependent equation in the y direction. Our delta y, well, our y final is 0. Our y naught is 7.5, so our delta y is going to be negative 7.5 minus 1/2 g is 9.8 t squared. And we can plug that in to solve for t. Negative 7.5 times, get rid of the half, we multiply by 2, divide by 9.8, and that's t squared, take a square root. So we figure out that our time is 1.237, etc. And then we take that value for time and plug it in to the x equation. To find how far away from the base of the building our object lands. So I just multiply that number by 5.7. I get 7.051. I should have 2 sig figs, so turns out it lands about 7.1 meters away. A lot of times, this is how a lot of problems go with 2D kinematics. You can use the y equation to solve for time, and then you plug that into the x equation to get a distance. As I've said, it's better to use the given values and not any values you calculate when you can, but time is the only thing that is shared by both our x and y equations, so if we need to use both parts to get an answer, we will often have to use the time that we calculate in order to figure out the answer to our problems.